Hi everyone, today we are going to be going over entropy and enthalpy and Gibbs free energy from Module 11. As a refresher, we're going to go over some basic definitions in thermodynamics. So we have energy, which is a thermodynamic property and it is the ability to do work. And entropy is the measure of molecular randomness or disorder and it is a state function. Enthalpy is again a thermodynamic property of a system, and it is the sum of the internal energy with the product of pressure and volume of a system. And so delta H is the change of energy in a system. Then Gibbs energy, it combines entropy and enthalpy into a single value, and it is the amount of energy in a system that is available to do work. And a spontaneous reaction is a process that will occur without the need of additional energy from an external force. Entropy and microstates. So we're going to talk a bit about how microstates and entropy correlate and what they have to do one with the other. But first we need to define what a microstate is. And in the Pearson textbook, it is defined as a specific microscopic configuration describing how the particles of a system are distributed among the available energy levels. And here, looking at Boltzmann's view of entropy and his equation here, you can see that with an increase of microstates, there is an increase in entropy. And so that's how they're correlated. And we also can see here the second law of thermodynamics, which states that all spontaneous processes include an increase in the entropy of the universe. Gibbs free energy. So how are we going to determine if a reaction is spontaneous? So the sign of the enthalpy or the entropy is not actually enough to know whether a reaction will be spontaneous. And so that's why we use this equation right here, which calculates the change in Gibbs free energy. And we calculate this by having the change in enthalpy subtracted by temperature times the change in entropy. And if that value is negative, then we know that the reaction will be spontaneous. If that value is positive, we know the reaction will be non-spontaneous. And this equation is valid under these two conditions, at constant temperature or at constant pressure. But what about temperature? So temperature is obviously a very significant part of calculating your Gibbs free energy. And if you know the sign of your entropy and your enthalpy, then that can change depending on the temperature, even if those are set. So we're just going to look at this chart here that has it nicely laid out. So first, when we're looking at our enthalpy, if we have a positive enthalpy with a negative entropy, the reaction has the potential to be either spontaneous or non-spontaneous depending on the temperature. So it won't be spontaneous at low temperatures, but it will be at high temperatures. If we have a negative enthalpy and a negative entropy, again we have the same possibility but just inverted from the first one. So it will be spontaneous at low temperatures and it will not be at high temperatures. If we have a negative enthalpy and a positive entropy, then our reaction will be spontaneous at all temperatures, both low and high. And if we have a positive enthalpy and a negative entropy, then our reaction will be non-spontaneous at all times. So it will never be spontaneous no matter the temperature. Okay, so now we're going to go over some practice examples just to reinforce everything that we went through or we just reviewed, and we're going to keep this equation here in mind in order to determine whether this reaction will be spontaneous or not. So with the first one, we're going to determine the temperature conditions in which 2NH4NO3 converted to 2N2 gas plus H2O plus O2 gas would occur spontaneously. So here we are given the enthalpy, and it should be noted that the enthalpy is negative, so this is going to be an exothermic reaction. Additionally, here we can see an increase in gas products, and this correlates with an increase in microstates. So this reaction is going to have a positive change in entropy. And so with a negative enthalpy and a positive entropy, we know that this reaction will be spontaneous at all temperatures. Okay, moving on to our next example, we're going to find the change in Gibbs free energy for this equation right here. We are given the enthalpy as well as the entropy, and the temperature that this reaction is going to occur at is 298.15 Kelvin. So noting that the enthalpy is negative and so is the entropy, we know that this reaction is going to be spontaneous at low temperatures and not spontaneous at higher temperatures. So in order to find the change in Gibbs free energy, we're just going to plug these values right into the equation, and keeping in mind that the entropy has to be changed into kilojoules, as that is the unit measure for Gibbs free energy. And so just plugging this in, we get a value of negative 1,484 kilojoules. And so because it is negative, we know that this reaction will be spontaneous at this particular temperature, which is 298.15 Kelvin. Okay, and because we see that this reaction has the potential to be both spontaneous and non-spontaneous but at different temperatures, we're going to find the temperature of inversion. So we do this simply just by setting the Gibbs free energy change to 0 and then isolating to find the K value, so the temperature. When the Gibbs free energy is 0, that is when the system is at equilibrium. So we're going to set Gibbs free energy to 0. We're going to take the same values that we used in the first case to find the change in Gibbs free energy. So here we have negative 1,648 kilojoules for the enthalpy. The same value for the entropy, still converting it to kilojoules, but now the Kelvin is unknown, the temperature, and so that's why we have just a K value there. So we're going to isolate by moving the enthalpy to the other side. It's going to become positive, and then we're going to divide through each side by our entropy here. And so with that, we get a final value of 3,000 for K, and so we know that at 3,000 degrees Kelvin, this reaction will no longer be spontaneous, and at any temperature above this, it will become a non-spontaneous process. Some real-world applications for thermodynamics. So obviously we use this in our everyday lives whether we notice it or not, but some simple examples are how water freezes below 0 degrees Celsius or how sugar dissolves spontaneously. As well, it's used in all kinds of vehicles, in cars, motorcycles, airplanes, pretty much, any motorized vehicle. And this works on the basis of the second law of thermodynamics, which we reviewed earlier. Thermodynamics is even involved in medicine. So cells are considered to be thermodynamic systems, which we can see here in the image. Cellular work gives off heat, and that interacts with the system outside of it. And this has opened a new branch of bioengineering thermodynamics, and this development in medicine has come with a lot of new different approaches and has helped with a lot of new discoveries. But all living systems waste energy in heat, and cells are spontaneously exchanging heat. Okay, so that's the end of this presentation. I've included here some links of videos if you want to learn more about thermodynamics or want some review or clarification, as well as the references that I used in putting together this presentation. Thanks so much for watching.